This is problem 3-46.m. It's on page 166. Compute the elongation of the square bar AB in figure P3-46 if it is 1.25, in other words 1 1/4 meters long, and made from aluminum 6061 T6. So there's a nice figure there below the problem statement. I'll copy part of it. I'm not going to write down everything. I'm just going to start by drawing the free body diagram. So you've got the problem statement in front of you. You realize that there can be reactions in the Y and the X direction. You realize that rod AB is pulling up on this to resist the load, which I will call P, which is 12.5 kilonewtons down. Now the amount of force in rod AB is what we need, because if we're supposed to calculate the deflection, then we're interested in the force, right? I mean, to calculate the deflection, the equation we have is that the stretch, or the delta, or the change in length, the amount that it stretches by, is FL over AE. Now sometimes it's handy to write this. Notice F over A is just the stress, so sometimes it's handy to write it this way. And both of these are on the equation that I referred you to, so they're both right there. What was it, 3.8? Was that the equation number? No, 3.9, page 128. It's equation 3.9. Anyway, so if we're going to calculate the deflection, how much this bar stretches, then we will need to know how much force is in that bar. So let's start with the statics problem and go from there. So I don't really care about what's going on at point C, so I will sum moments about point C, taking counterclockwise as positive. Of course, those moments had better sum to 0, otherwise we've got a dynamics problem, and this is the wrong class. Okay? You'll get to that eventually. All right, so summing moments about C, we're going to have the force in rod AB that's pulling up on this beam, and the distance from here to here. Can you read that off for me? 2.5. So it's 2.5 meters. You can put that in your notes if you want. For now, I'm going to stick with symbols and note that that is the distance between C and B. I did this so that you'd see how I typically will indicate distances between 2 points. I'll write the 2-point names and put a bar above it to indicate the distance between them. Okay? So there's the moment of FAB, and notice it's a positive moment. Then we have to subtract off the moment due to load P. Now that distance is 4 meters, but again, I will write it as P times the distance between C and D. Did I get those points right? Okay, I think I did. So basically, I want to solve for the force in rod AB. It would be equal to P multiplied by the distance between C and D divided by the distance between C and B. Okay? So, load P, 12.5 kilonewtons, multiplied by the distance between CD. Well, CD was, you told me, 4 meters, right? CB was the 2.5 meters. Notice the meters go away. We'll be left with kilonewtons. When I plug this into my calculator, I think I did it right. I got 20 kilonewtons. Does that seem reasonable? You can plug it in your calculator if you like. So that solves this part of the problem. Now we know how much force is in rod AB. Let me get rid of this part. Let's start plugging in numbers here. So 20 kilonewtons. That's the force applied to the rod. What is the length of the rod? Well, we were told that the length from A to B, because B is just this point here, C is here, D is here, and A is up here at the top of the rod. The distance between A and B, the length of the rod is 1.25 meters, 1 1/4 meters. And then we need the cross-sectional area. Well, we were told that the rod is a square rod. It's 20 millimeters on one side, so it must be 20 millimeters thick. So that would just be 20 millimeters squared is the cross-sectional area. And then finally, E, elastic modulus. Well, they didn't give that to us. Where can we find it? Back of the book, that's right. Go to the material properties at the back of the book. If you want to find properties of aluminums, that is not page 714 or 715. 716 looks interesting, but it's not aluminum. Structural steels. Page 718, appendix A18. Typical properties of aluminum alloys. If you notice, they don't list any elastic moduli. You know why? Because it's a footnote at the bottom of that table. Because the elastic modulus of aluminum really is not sensitive to the alloy and temper. So look at the bottom of the page for the footnote. Elastic modulus for most aluminum alloys, including a bunch of them, is 69 gigapascals. Okay? Does everybody see where I got that from? Okay, questions? We're doing okay? All right. Now, what is a kilonewton per millimeter squared again? Do you recall? It's a gigapascal. So the kilonewton per millimeter squared is going to cancel with the gigapascals and we'll be left with meters. Does that make sense? We still have to square the 20. Okay? Now, I've already done this, but for practice, plug it into your calculators and see if you get the same number I got. Plus, I was doing it in a hurry, so let's make sure I didn't hit a wrong button somewhere. 4.3. Do I have a second for 4.3? Don't forget to square the 20. I may have done it wrong. I don't think so. How much? Tell you what, let's do this. Let's write them down. What did we have? What was the first 4 point what? 4.4? Okay. What else? What other number did you tell me? 0 point something.
0.0009.
309. Okay. And I assume that's meters. Anybody else?
4.3.
We've got a second on this one. We've got a 4.3, which is about 4.4. We've got basically two people saying 4.4. We need a tiebreaker. Oh, 9. All right, there's our tiebreaker. That's what I got also, is the 309. My guess is you may be forgetting to square that 20. Okay? So 20 times 1 1/4 over 20 squared, which is actually 400 over 69. Okay? In fact, I got 30906, but it doesn't matter. So it looks to me like the deformation is 0.9 or so millimeters, which seems reasonable. So almost a millimeter of deflection. Now, as it deflects, what's going to happen to the mechanism? Well, this end's going to move down a little bit. We don't know how the forces move. This is at a slight angle, so there's a little bit difference in distance here. Does it really matter? No. We're going to neglect small changes like that. You'll notice that a lot of times in this class, when we calculate a deflection, we'll basically neglect the effect of that deflection on how the loads and everything are really applied. Does that make sense? So small deflections is one of the big assumptions in this class. Any questions on this problem? All right.